Okay, today we are going to continue our look at the world of rotation. Specifically, we're going to be looking at moment of inertia and how the resistance to rotation depends on the way the mass is oriented about the axis. So one of the things that we need to really consider is that when we are looking linearly, the way that we move is based upon our mass. Our mass is our resistance to our change of our motion. So, Newton's second law, F equals ma, your acceleration is determined by the force applied and how much your mass is. So when we look at that resistance to rotation, what we call the moment of inertia or the rotational inertia of an object, and you'll also hear me call it moment of inertia, which I abbreviate as MOI, that resistance to rotation is based upon how the mass is distributed about the axis of spin. So when we look at the total rotation of inertia of a single particle for a system, if we can treat that particle as a point mass, the moment of inertia for a point mass is just going to be its mass times the distance it is from the axis of rotation squared, or mr squared. If I have several of these particles, I add all of those up. So I have the sum of mr squared. M is going to be the mass of each individual particle, and the r is going to be the distance from that particle to the axis of rotation again. So we're looking straight line. Now, when we look at kinetic energy linearly is 1/2 mv squared. Well, you may remember that conversion where we said that v is r omega. So it's going to be r omega quantity squared. So that's going to give us 1/2 mr squared omega squared. So if I was looking at a point mass, this piece right here is my I. So I have 1/2 my resistance to rotation omega squared. And now recognizing that that resistance to rotation can be used now for any shaped object. So that I is the moment of inertia for the object we are looking at. So we have a rotational equivalent. So as we scroll down our page, we had this example. And so we can look at these individual objects. So if I wanted to calculate the moment of inertia for the first one, keeping in mind point mass, we're looking at mr squared. So we're going to have 36 kilograms times 1 squared. So that's going to give me 36. Now my units for rotational inertia are going to be kilograms because we had the mass, and then we're going to have a meter squared because we had that distance squared, so it's a kilogram meter squared. If I look at this second particle, using that same equation, the moment of inertia is going to be 9 times 2 squared. So it's going to be the same, 36 kilograms meter squared. If I look at this third one, moment of inertia is going to have to be 4 times 3 squared. Again, we're going to get 36 kilograms meters squared. So it's important to realize that even though you have different masses, you could have the same resistance based on where you are located at. And so if we look down here just a little bit further, if we have a rigid body that consists of a lot of connected particles, like a frisbee, we can calculate the rotational inertia using this integral. Now, some of these have been calculated for you, and we're going to look at some of these a little bit closer. So these are 9 common shapes. We have just a hoop about a central axis. So that is a thin hoop. We assume infinitesimal thickness. Then we have an annular ring, so it has an inner radius and an outer radius. We have a solid cylinder or a disc, because a disc, remember, is just a really short cylinder. So we are rotating that about the central axis. Then we have it about the center diameter. We have a thin rod. And then we could look at a sphere or a spherical shell. We could spin a hoop like we kind of spin a coin. And we could look at a rectangular slab. So let's look at these a little bit closer. So we are going to start with the simplest example, just a hoop about a central axis. So we're going to look at that integral. The integral is the integral of r squared dm, and that's going to equal our moment of inertia. Now, what do I mean by a dm? Well, that means that we're going to look at an infinitesimal mass. We're going to just take a piece of that loop, and it has a little smidgen of a mass. Now, for this example, you know that radius is constant. That radius is big R, so I can bring that out front. So I have r squared, the integral of dm. Well, that's going to be the total mass. So that's where we get mr squared. Now, if I kick it up a notch and I look at this annular ring, the first thing we have to realize is that this mass is spread out over a volume. Well, how am I going to find that volume? I'm going to be calculating basically the cylindrical shape, the shell. So I have to realize that we're basically going to be looking at mass density, mass per unit volume. So that's going to be the mass of the ring. Now the volume of the ring is going to be pi times the length. I'm going to call that L. I'm going to have my outer radius squared minus my inner radius squared. That's going to be r2 squared minus r1 squared. So that is going to be equal to our infinitesimal mass over our infinitesimal volume. So we're going to look at it, just that little bit of piece, that density is going to be uniform. So now how do I get that here? Well, we think about this, we're dealing with a ring, so this is going to be equal to infinitesimal mass. We're going to have 2 pi L radius with respect. So for a cylinder, we're looking at pi r squared times the length. When I take the derivative of that, this is what comes out. So that we're going to then solve for dm. So mass divided by pi L r2 squared minus r1 squared. I'm going to multiply it by this, by that 2 pi L r dr. That's going to equal my dm. So the first thing we're going to do is we're going to make that substitution to get it to something that's changing. That radius is changing as we go through this. So this integral is going to become the integral of r squared times mass times 2r dr over r2 squared minus r1 squared. We're going to take all of the constants and we're going to dump those out front. So we're going to have 2 big M r2 squared minus r1 squared. And then we're going to look at the integral of what's going to become r cubed, r squared times r dr. Now, where are we starting? Well, we're starting at the inner radius, r1, and we're going to end at the outer radius, r2. So we don't do a lot of definite integrals, but we are doing one here. So we're going to have 2 times the mass, r2 squared minus r1 squared. And that's going to give us times what's going to be r to the 4th over 4. and we're going to evaluate that from R1 to R2. So we're going to have 2 times the mass over 4 times R2 squared minus R1 squared. Now when I evaluate this definite integral, what I'm going to get is R2 to the fourth, so I'm going to substitute that in first, top minus the bottom. Now you're probably thinking this looks absolutely hideously evil. There's no way I can simplify this. Oh, but we can. So 2 over 4 is going to give me 1/2. I'm going to have mass R2 squared minus R1 squared. Now this to the fourth, this is a difference of perfect squares. So go back and channel Algebra 2 class. This becomes R2 squared minus R1 squared times R2 squared plus R1 squared. Well, the R2s minus R1s are going to cancel, and this is going to leave us with 1/2 mass R2 squared plus R1 squared. That, you'll notice, is the handy equation that's right here. So let's look at a disk. Let's clear this up and we'll look at a disk. So here we have a disk. We are again going to look at the integral of r squared dm. That's going to give us our moment of inertia. Now again, we're going to look at that mass per unit volume. Now this is a solid cylinder, so our volume is going to be pi big R squared times our length L. Our mass is going to be m, and when I take the derivative of this, if I look at the infinitesimal mass over the infinitesimal volume, I'm going to get dm over 2 pi r L dr. So again, I'm going to set basically this one and this one equal, and I'm going to solve for dm. So I'm going to get m over pi r squared L times 2 pi r L dr. That's going to equal dm. The L's are going to cancel. The pi's are going to cancel. So what I'm going to get is the integral of 2 big M R over R squared. That's going to be then times little r squared dr. So everything that's a constant is going to come out front. So it's going to give me 2 big M over r squared. That's going to give me the integral of r cubed dr. And we are going to go from where we start, which is at the center, to where we end with our mass, which is out at big R. So that's our limits. So we're going to get 2m over r squared. We're going to have r to the fourth. It's going to be lowercase r. So r to the fourth over 4, evaluated from 0 to big R. So that's going to give me 2m over 4r squared. Now when I evaluate, I'm going to put big R in first, then I'm going to put the 0 in, and that's going to give me 2 over 4 is 1/2 mass over r squared times r to the fourth. So that's going to give me 1/2 mr squared. And so this is kind of like where we go with all of these derivations. Now, we have some of these standard ones. The questions I always get is, should I know these? How much do I need to have memorized? So I'm going to say you absolutely should have a point mass memorized. That one should be cold. The disc one should be close because we always look at merry-go-rounds or something that has a disc. And you should know a rod. Those are the big three. If you know those three, typically we can derive the others if we need to. So when we come back, we are going to look at the parallel axis theorem and how we can move the rod axes around.